All right, how's everything going? Good. Any questions? PA5 okay? Yeah. Trying to figure out the inventory?
I'm trying to figure out how to like how to initialize that.
Mm-hmm.
I haven't figured it out yet.
Write a loop.
That is it.
Yeah.
There's some code.
So your return from Maxval is probably something like this. Whatever you want to call it, but something that will give you the actual value of your solution and the counts of each item that get you to that value, right? And to initialize this, right, you want to set your value to 0, you want to set your counts to 128. So you can make like an init function that that just clears all of those out. You may be able to do that. I don't actually know if that works or not inside a struct. I suspect it doesn't, but if it doesn't, just go through a loop and set them all to 0 to begin with. And then maxval. Maxval takes an integer capacity and it returns one of these structures. That is exactly like if you're just returning an int, except it's also got a handy inventory of how you get that value out by putting items into your bag. And so once you know that so say maxval of 10 equals item 3, value of 3 plus maxval of 10 minus weight of 3. Right, let's say this is what you were doing in the version that's not keeping track of items, right? So if you take 10, take away the weight of item 3, find the maxval of that, add the value of item 3. Let's say that's the maximum value you can get out of 10, right? So this is also going to return to you an item count, how many you need of each item. Right, so there's some number coming back from maxval. So the maxval that you return from maxval 10, just increment that count to say, hey, we got one more item 3, and increment the value you get back from maxval 7 by the value of whatever that item is. So if we're just returning values, you take the value of this and you add the value of item 3. If we're returning inventories, take the inventory that gets you this and add 1 to the count of item 3. And that's the value you return from your outer call to maxval. We're going to do a rod cutting problem on the board in a minute, which might help also. So if you go through your loop and you find that item 3 is the one that maximizes this expression, right, then our final value for maxval 10 is the max value from this diminished capacity plus the value of item 3. The inventory for the maxval is the inventory for this plus 1 more of item 3. So take the inventory you get back from this, increment the count for item 3, return that as the inventory for your original maxval. So we did basic rod cutting yesterday, right? Okay, so I want to have you do this on the board in groups, work through one of these problems. And I'm going to give you a pricing table for cutting a piece of rod. And I worked this out at breakfast, and it looked like pretty good numbers. So let's try this. So let me show you what I want you to do for these max vowels. I'm going to do max val 6, but I want you to do this for max val 5. Okay, but let's say that we were working with a 6-inch piece of rod. So max val of 6 is the largest of the following. Well, if we cut off a 1-inch length, I guess I should put a value in here for 6. We'll say that 6 is worth 35. Okay, so max val 6 is the largest of the following. I can make a 1-inch cut, which gets me $4, and then leaves me with 5 inches to cut up. I can cut a 2-inch piece, which gets me $6, and leaves me with 4 inches to cut. I can cut a 3-inch piece, which gets me 14, and leaves me 3. I can cut a 4-inch piece, which is 16, and leaves me 2. I can cut a 5-inch piece, gets me 21 and leaves me 1, or I can cut a 6-inch piece, which leaves me 0 inches. So if I can calculate these 6 expressions, I can find the largest. That's the value of max val 6, and I can write in what that is. Okay, so what I want you to start with on the board is, as neatly as possible, do the same kind of thing to figure out what max val of 5 is. And you'll come up with 5 expressions involving max val 4, 3, 2, 1, and 0. And once you've got that and you're sure it's right, then go ahead and make a new column and figure out max val of 4 and so on, and work your way down to the base case. And the base case, max val of 0, we'll just assume that's 0 because you got nothing to sell. So find a spot on the board, find some people to work with, and start by trying to find the expressions for max val of 5, and then work your way down to 4, 3, and 2, and 1. And let's see what we end up with. Say what? That was for a rod of length 6, right? But in general, it's the value of item I plus max val of whatever your length is minus the length of item I. Right, so this first expression is saying if we have a length of 1, right, we get the value of that, which is 4, and then our length decreases by that 1, so it's max val of 5 plus 4. So for 5 inches, you get 5 expressions.
Why do you say 4, not the 6?
Because 4 is, we're cutting that 1 inch off of the 5, so that's what the value of the 4 first thing there is. And then the remaining rods, max val.
You're finding the max value, but you're doing it the way your code will do it, which is by calculating the 5 expressions that you have for this largest of.
And one has 4, 6,
16.
Yeah.
Yeah, because this 4 is just minus 1. And then this 6 is just minus 2 for the original.
understand why we start at the 4, not the 6.
So the 6 is the value of taking a 2-inch length rod.
Yeah.
So when we're taking up 2 inches, we're subtracting 2 from 4 length, which
Okay.
gives us 2. So we're just going down
Yeah.
the list of lengths
Right.
in order of shortest to large.
Largest of one is just 4.
He's going in a different direction.
Because when we get to
Opposite
the
direction.
longest, it will, when the length that we're taking equals the length that we have when it equals 0.
Why do we start at 4?
Say what?
Why do we start at 4?
That first expression is saying, suppose I cut 1 inch off this bar. Okay, a 1 inch piece I can sell for $4. I've got 4 inches left. I don't know how much I can sell that for. But the best I can do is whatever my max val function of 4 tells me.
Oh.
So that's the value of 4 inches for $4 for 1 inch, and then whatever I get for the other 4.
So and the max one of 4 is the things we left after we cut off that.
Yes.
Okay.
And the second line we cut off 2 inches, it's worth 6, and we've got 3 inches left.
Okay. Cool. Thank you.
Yeah.
Yeah, 6. Yeah, 6 is just about 6 plus these two. So it will, 14 here. Myself. 2 is either 4 plus. Well, we know what the answer is. 4 plus 4 plus 4 or 6. Yeah, you're right.
Yeah, we're putting 1 inch.
This is 4. This is 4. And this is 8 plus 4. Now we're going to go. Okay, now let's find this one. No, you run our check.
How far have you guys got it on?
Okay, no. Well, it's like, why do we need to know these if we know which ones are high? Once we find out each one of these first.
No, because now we can compare it with these numbers.
Well, you'll see. This one, let's see.
With the dynamic.
Okay, this one's 16. What's 14 plus 4? Right, which is what? 18. 6 plus 2. So it's just going to be.
Oh, got it.
Yeah. Okay. And then max val 5. We're just going to do this. So this is 21, 16 plus 1. Yeah, I don't know.
Am I getting this?
18.
Good.
So in our program, what are we, for returning the items, what if it's executable?
And then what about
Yeah, when you compare your actual value, if you have 2 of them the same, depends how you write your code.
No, this isn't that hard. So you gotta go all the way down.
Cool.
Yeah, I have that issue. Then what you're doing is you gotta go through every item. This is every item. So you gotta go through every item. So that's the fourth one.
All right, so did you finish this up?
Yeah.
So what's max val 0?
Like it chooses the first one to 0.
Yeah. So what's max val 1?
Like, what about the next one? I know.
Okay. So we're going to write that down.
Chop off 11
No, I mean right now what max val 1 is.
Our group's barely up through the dividing up.
We do.
All right, so what's
I
max
thought
val
I
2?
was right in.
Yeah.
We've got the function working without the infrared.
tried to write that up.
Wait, why did this?
Between that one is
How do you get segments?
MD5.
About one, get too early. So we've got. Okay, I only did that large.
All right, so keep working your way back. You'll get to max val 5.
It's not actually going through all the items. It's just text the first value.
And you can simplify this. You actually know max val of 2 from what you've written, because max val of 2 is the largest of those two numbers, either 8 or 6, so it's actually equal to 8.
A list of strings. That's what we have. Yeah. So then make sure you ingest the list first, the list of strings, and then go through that. And for each of those,
Cool.
grab it and then store it.
And are there 2 ways to use it?
Yeah.
I guess. And then it's gonna
Good.
I'm just working.
Yeah.
Because there's
Yeah.
That's what you do. So which way would the max out? Which way would be
You enter code. So if you do it like this, which is starting from like 20.
starting on top. Go to the bottom.
Yeah.
It would start with the 3 to 1.
Yeah, as long as you strictly greater than your best. Say greater than or equal to, and then grab the last one. Okay.
Just in the back hall.
That's fine.
All the select values.
Yeah.
Then it will break this forward. I mean, it's gonna be instructions, so it'll take a hell of a lot. I'm thinking more than like, wise, if you try to store it out there, or make it, probably not see that many. I'm thinking in like extremely large scale stuff. Should have been extremely large. Taking more. 2 kilobytes of mine. 2 kilobytes, oh, actually? Yeah, that's it. That is huge.
All right, is this making sense for everyone? And yeah, sometimes you'll find 2 things that give you the same max val. That's okay. If you're just looking for the maximum value, it shouldn't matter which one you pick. So it may help to actually write down your max val for each of these. So what's max val of 2 equal to? Okay, so you can put 8, like, you know, oh, you got it down there, sorry, you're good. Okay, so yeah, so what are your 5 expressions here?
Yeah, so you're right. I thought there's a way around it. I know. Oh, yeah, you're like, there's a way around it. Like, come on, that's wait. I guess I'll see what I know. It's all there.
Cool. Does that make sense? All right. You got it. Does that make sense? Say it again. Oh, yeah, let's talk about that. So, so you got 22, right? And you start with a max val of 5. And so, oh, I was going to copy yours, man. So 4 plus max val of 4. Uh, 6 plus max val of 3. 14 plus max val of 2. 16 plus 1. And 21 plus 0. Right, and so there's more branches, more levels to this tree as we continue to solve these sub-problems. In the end, right, you've decided that, you know, the max val of 5 comes from, I don't want to try to make this real because I'll mess up, but it comes from this branch down here. And the max val of 4, let's say it comes from this branch down here, and the max val of that comes from this branch, and let's say the max val of that comes from this branch, right? So if you know the path of recursion that you took to get to the final maximum value, that contains the solution, right? The way that you achieve that maximum value. Because this edge over here is the edge that corresponds to cutting off 1 inch, and this line right here corresponds to cutting off 2 inches, right? Just the way that we're envisioning the while loop. So this is the 1 inch cut, 2, 3, 4 inch. And so by knowing the path you took to get this final maximum value of 22, that's the collection of cuts that give you that result. And if there's multiple paths that give you the same max val, right? Those are just different ways that you can achieve those cuts. And not every path through here is necessarily unique, right? Cutting off a 2 inch piece and then selling the 3 inch piece is exactly the same solution as cutting off a 3 inch piece and selling a 2 inch piece. So you'll see multiple ways of getting your 22, but not every one of those ways is a distinct set of cuts. Okay, so does this help at all? Right, and it's really just another version of knapsack, except knapsack we don't have this nice, you know, inventory where every single length has a value, so you have to go through and pick those out. But it's exactly the same process. But we get the inventory of items by keeping track of it as we go instead of trying. We don't actually recurse this. We don't actually traverse this tree ourselves, right? This is what's happening through the recursion. And with dynamic programming, right, the first time you calculate M of 4, it's going to require M of 3, and then we're never going to do any of these recursive calls, and we're never going to do any of these and any of these, and we're just going to knock off most of the tree. So that's what your dynamic programming is saving. The other comment on I think this was what we were talking about. So when we're returning a result, make sure you update your array where you're saving your results, your dynamic programming piece. That's not an array of integers anymore, it's got to be an array of struct results. Because we're using this array, this memory, to save us from having to actually call maxval. Well, maxval returns a struct result, so your save array has to have struct results in it also. Otherwise, you don't know what the inventory is for each of your subcalls. So you have to update your save array, and then you have to change maxval to return a struct result. Yeah. All right, so any other questions on that? Let me run through red-black trees a little bit. This is a different type of balanced tree. And we didn't get to this yesterday because I had you do your survey. So, we talk about red-black trees just as an illustration of a different type of balance, and then we'll go back and we'll start looking at egg dropping in more detail. So red-black tree. So this isn't a search tree, it's a binary search tree. Okay, everything on the left is smaller than the root, everything on the right is bigger. Nodes are limited to 2 children, and there's a root, so all the same as usual. It has the additional feature that each node is colored either red or black. So you have typically 1 extra bit in the node somewhere that says what's the color of this node. And there's different stories why they're red-black trees. One story is when they were working this out, all they had was a red marker, a black marker. But I don't think anyone knows the truth. So they're called red-black trees. All right, so there's 5 properties to a red-black tree. First property, each node is either red or black. So there's a color associated with a node. Second property, the root has got to be black. So root node is always colored black. Third property, the leaves are what we call nil. And they're also black. Okay, so what does this mean? Suppose you have a tree like this, 20, 10, 30. And we have this notion that sometimes things have 1 child, sometimes they have 2 children, sometimes they have no children, right? So in this case where there's no descendant, we actually imagine 1 extra child, which is called nil. So these are basically our null pointers. But it means that every node has 2 children exactly. And some of those children might be null. But we actually sort of think of those as part of the tree. And then we insist that all those nil leaves are black. It's like null. Except null we think of as like not being there. So red is coming up now. So if a node is red, so each red node has only black children. So a black node can have black children or red children, but a red node has got to have only black children. Okay, so there's a definition in here before the 5th property. So the number of black nodes from the root to a node n is called n's black depth. So normally the depth of a node is how many nodes there are from the root to that node. The black depth is just how many black nodes there are from the root to that node. Okay, so it's a modified notion of depth. So property 5 is all leaf nodes have the same black depth. And And we call that number the black height of the tree. And property 5 is the one that, property 4 and 5 together are the ones that really make this thing work as a balanced tree. So 5 basically says if you start from the root and you go to any leaf, you're going to encounter the same number of black nodes, no matter what leaf you go to. So let's look at some red-black trees. So, and I'm not going to worry about numbers, I'm just going to draw the circles. Oh yeah, this is really hard to see on there, so I'll label these. So here's black, and here's black, and here's black. Perfectly fine red-black tree. In fact, if we make an entire binary search tree out of black nodes, and it's balanced, it's going to be a red-black tree. Okay, as long as we have that uniform number of nodes. So a perfectly balanced binary search tree is a red-black tree. I can add more nodes like this, and that's still a red-black tree. Okay, this is also a red-black tree. So every node is red or black, the leaves are all black, the root is black, every red node has only black children, and the black depth of each leaf is 1, 2, 1, 2, 1, 2. But it's not perfectly balanced like this tree, right? There's more stuff on the left. So is this a red-black tree?
No.
Why not?
There's a black nodes.
There's a what?
There's a black node with black nodes.
Oh, that's red, sorry. Thank you.
Okay.
So is that a red-black tree? Right, red nodes all have black children, root is black, leaves are black. It's the black depth that's usually tricky, so 1, 2, 3 to any of these, 1, 2, 3 to any of those. But it's definitely not like perfectly balanced in a classic sense, right? Because the total height over here is 1, 2, 3, 4, 5. Over here it's 1, 2, 3. So a question is, how bad can this look and still be a valid red-black tree? So suppose D be the black depth. So we have a tree and every leaf node has to have D black nodes from the root down to that node. So in terms of total number of nodes, ignoring the color, what's the shortest possible number of nodes I could have that would still be a valid red-black tree? So shortest path from a root, following nodes down until I get to a leaf, and the black depth is D. What's the fewest number of nodes that I might find ignoring color? It's a slightly silly question, but we're working on definitions here, so it may not be obvious. Oh, that would only work if the tree had a black depth of 1.
So the question is, how big is the depth?
So if the black depth of the tree is D, what's the shortest path I could possibly have from the root to a leaf node?
D.
D. And what would that path look like? What colors? If they alternate red and black, I think there'll only be D over 2 blacks along that path. And since the black depth is D, there's got to be D black nodes. So black to black to black. So if I have a path from the root to a leaf that's every node in that path is black, that's the shortest possible path. And that's going to have D nodes. Okay, what's the longest possible path?
2D.
Yeah, so that's where we alternate. All right, we can have a root. And since the root is black, it's perfectly fine if that has a red child. But once we have a red node, it's got to have a black child. But then that can have a red child, but that's got to have a black. And so on. And if we do this until we have D black nodes, the total length of this is going to be 2D. So that's how bad the tree can get. It's possible that the shortest path from the root to a leaf node has only D nodes, and the longest path has twice as many. But it's still a red-black tree. So classic AVL tree, a balanced tree, the requirement is the height has to be within 1. Right? So we're basically constraining the path lengths to be plus or minus 1 of each other. Here we're constraining the path lengths to be a factor of 2. So if one path is 100 nodes, it's perfectly legal if the longest path is 200 nodes. It can still be a red-black tree. But it can't get totally crazy. We can't have 100 nodes over here and 500 nodes over there. That would be considered unbalanced. So this is similar to an AVL tree in that we have these criteria we need to satisfy. In an AVL tree, the criteria is the balance factor has to be between 1 and minus 1. Here we have a more complex set of criteria, but there's going to be more cases when we can insert a node and not have to do anything. Right? Because we can start piling up things on one side or the other side and still have this be a valid red-black tree. And there's no explicit requirement that the longest path can't be more than twice the shortest path, or the tallest height can't be more than twice the shortest height, but buried inside these requirements, which are relatively easy to work with, is this constraint on the height difference. And as long as we stay within the bounds of that constraint, we can say things about the performance of this, and we get our nice n log n behavior. And so using a red-black tree, coding this is just a matter of when you insert a node, for example. You insert a black node, right, because it's a leaf. And then you make sure that you're not violating the black depth, right, which means you may have to recolor the node or recolor a red parent. And so on and so forth. And so there's a series of adjustments you have to make, and that gets really convoluted. And I'm not going to go through how we do insertion or deletion, but it's a series of different cases. And you have to look at your parent node, you have to look at your grandparent node, and you have to look at your aunt or uncle node, right, a sibling of your parent, the other child of your grandparent, to know whether you violated any of these conditions, and if so, what you have to do to adjust it. And you do something similar to a rotation, including recoloring nodes, and you can restore these in a fixed amount of time. All right, so I'm not going to ask you to do anything with red-black trees. I'd like you to know that a red-black tree is a balanced tree, and that the main notion of balance for a red-black is this 2x factor on the path length. Yeah?
Did we discuss the purpose of the red-black tree?
It's just another way to balance a tree,
Oh, okay.
or to maintain a tree that gets you this n log n behavior. So usually when we're balancing, we're trying to avoid these big long linked lists that we call trees that are order n, or n squared. And this needs work less frequently, but might need more things done when you have to do work. But in general, I think you can insert more things into it and still not have to rebalance it. So it's a better behaving thing. And it's just one of several types of balanced trees. There's B trees, there's 3-4 trees, there's lots of different approaches to trying to maintain this n log n behavior. And in a probably third year data structures course, you could spend a few weeks just taking apart all kinds of different tree balancing algorithms. All right, good. We got 6 minutes. Let's talk about egg drops. So remember the setup, right? We went through the setup yesterday, right? We started this. Okay, so you got a basket of eggs. They're all identical. They're idealized. They're reusable. And you've got a series of floors, and you want to answer the question, how many experiments do I need to find what the critical floor is from which eggs will survive and above which they will break? And we want to write a function egg, which takes a number of floors and a number of eggs and tells us how many experiments we need. And we can name a few base cases. So if E is equal to 1, I think we talked about this yesterday. So how many experiments do we need if we only have one egg? We need F, because we got to start from the first floor and work our way up. If we don't start at the first floor and the egg breaks, we don't know what the critical floor was. So if E is equal to 1, we can just return F. If F is equal to 1, single floor in the building, how many experiments do we need? Just one. Drop the egg. See if it breaks. If F is less than 1, we don't have to do anything, because there's no floors to drop the egg from. I don't know if we need this case or not. Otherwise, we got to do some experiment. We got to take one egg, we got to bring it up to some floor, drop it, and then make a decision based on the results of that experiment. Okay, else return 1, because we're going to have to do one experiment right here, plus the smallest of what we're about to describe. Yeah. Because if there's F floors, there's F possible experiments we can start with. We can say, okay, first experiment, we're going to drop the egg from floor 1. Or first experiment, we'll drop from floor 2. Or we'll drop from floor F. So we want to know for each of those possible first experiments, what's the best we can do in terms of how many experiments we need to run. So this is like for I equals 1 to F. Drop from floor I. Well, suppose we take our egg, we go up to floor I, and we drop it. So if the egg breaks, what can we conclude? We go up to floor I, we drop the egg, and it breaks. What does that tell us? Not to do it from that floor. Do we have to test a floor above that? It'll still break. So the critical floor is somewhere below floor F. Could be below I, could be I minus 1, I minus 2, could be the first floor. And we lost an egg. So however many eggs we have left, so E minus 1 and floor minus 1, this function tells us how many experiments do we need to find the critical floor for this setup. So if the egg breaks, this tells us how many experiments we need after our first experiment we already did to answer our question. On the other hand, if the egg survives, well, the critical floor is somewhere, sorry, this is I minus 1, because we dropped from floor I. If the egg survives, the critical floor is either I plus 1, I plus 2, all the way up to F. So we have a new subproblem, right? We basically have F minus I floors, and we still have E eggs.
Is it F minus I, not I minus 1?
It's I minus 1 if the egg breaks, because we have to start below the floor that we just used. But if we drop from floor 10 and it survives, we can start testing from floor 11, 12, 13, all the way up to the top, which is like floor 100. So it's the total number of floors in the building minus the floor that we just dropped it from. And we still have E eggs left. And so one of these will tell us how many experiments we need, depending on whether after our first experiment the egg broke or the egg survived. Since we're looking to guarantee a number of experiments, we actually need the max of these. So you loop through all the floors. For each floor, you make these two calculations. You find the maximum of these. You find the smallest of all of those maxes. You add 1 to that. That's what your egg function has to return. And it's no different from rod cutting or knapsack or anything else, right? We're taking this function, we're expressing its value in terms of other values of this function. But in both of these, either the number of eggs or the number of floors is decreasing, which means eventually either E will be 1 or F will be 1 will pop out of our recursion. So this will eventually come back and give us an actual answer. And I'll show you some code for this tomorrow. I'll leave you with a shout out for Ackermann's function, because this starts to look a little like Ackermann's function. So if you haven't looked this up before and you got some time, look up Ackermann's function on Wikipedia. It's a fascinating subject. It's a simple recursive function, and it takes you into entirely crazy branches of mathematics of large numbers and things like that. So, and it's on par with what the egg drop function looks like. All right, so we'll look at some code for that. We'll do Oracle of Bacon tomorrow. We'll do some Huffman coding and some decision trees, and wind up on Friday.